Okay, hi everyone and welcome. So today is actually 111th birthday of IBM. Yes, so thanks everyone for joining, and also welcome everyone who joined us remotely on WebEx. So let me start by giving a quick introduction of who we are and what's our mission. So we are actually a Silicon Valley Technical Vitality Council group, and our goal and mission is to get together IBMers for some events, for some talks, and actually get together to solve some problems and share together the recent trend in technology. And we are also Bay Area Academic of Technology affiliates. So if you are also interested to join as one of the affiliates, please reach out to us. So today we have a tech talk by IBM Research, and the topic is Future of Computing. We have Dr. Jeffrey Welser with us, who is going to present. So let me also talk about the Silicon Valley Technical Vitality Council a little bit in more details and about the items that we are doing. As I mentioned, we do a lot of tech talks. So last month we had someone from IBM Research who talked about natural language processing, and there is a Slack channel for IBM internal folks to join, and you can get updates about the upcoming talks and let us know if there is any particular topic of your interest that you want us to invite subject matter experts to talk to you about it. And there is some trends that IBM is actually doing in research and technology. One of the programs that we have been doing is Jumpstart program, which is for new hires, and it actually helps them with networking in the company, and they will get some opportunity for public speaking, and they will also get some mentorship. We also have some patenting opportunities, and actually I'm planning to have this topic in one of the upcoming sessions, because as you know, we are one of the top companies in terms of the number of patents and the new ideas that we come up with, and there is a very good support by IBM leaders to give us a lot of good resources and help us with patenting. So I'm going to schedule a session and walk you through how can we do that. There is also a Hyperblue program for startups, and actually there is also a program called Mass Challenge, in which the new startups, which are not IBMers, I mean, they can be IBMers who go and have their own startups, but this program is for new startups who want to get some mentorship. For example, I have a 101 mentorship meeting with one of these startups and guide them through and brainstorm on their data science problem. Also, we provide them some free cloud accounts to run their process, and also help them with some guidance on how to progress from their business side. And also, the last item is open source. As you know, IBM has been a huge fan and founder of open source technologies. Actually, myself, I'm part of the Center for Open Source Data and AI Technology, and we have been contributing to a lot of technologies so far, like TensorFlow, Keras, and a lot of other technologies in open source. And as we are the leaders in the space for many technologies, we really believe that we have to give back to community by contributing to this and let others also use the technology, because it's not possible to do it like stand alone or individual. I think the power is when all the companies or all the great people in the industry or technology come together and share their knowledge. So with that, I introduce our speaker for today, Dr. Jeffrey Welser, and we are very honored to have you here. So he is actually the Chief Operating Officer for IBM Research and Vice President. And so with that, I will hand it over to you, Jeff. Thank you.
Thanks very much for having me. I've got to kind of stay near the podium, I guess, so that I can keep the WebEx folks hearing my voice. Hopefully you guys can hear me okay in the back. Great, excellent. That's a good thumbs up there. So yeah, so I'm Jeff. I actually started with IBM 27 years ago, so I'm not quite 111, but I'm getting there. Nonetheless, I've been in research for most of my time, but I've also spent some time in development organizations and in corporate along the way. My background is semiconductor chips and physics, so I'm kind of more of the hardware side of the world. And when I started, IBM was still doing a lot of hardware. Now we obviously do great hardware in Z and P, but we have about 2/3 of our work now in services and consulting. So I'm going to talk about a couple things. Really, I'm going to focus on what we're doing in research, but with the framework of sort of what we see as being sort of the next big trends going on in computing. But to start off, I mean, the research division, for those of you who aren't aware, is a separate division in IBM. It's a little bit different than many companies. My boss is Dario Gil. He's the head of and the senior VP for IBM Research. He reports directly into Arvind. So we are not connected specifically to any business unit. Instead, we are charged with supporting all of the business units' development needs. So from research, we should be trying to do what's necessary to keep those pipelines full. You can see the locations. We have about 12 labs around the world. The headquarters is back in New York, Yorktown Heights, New York, which is just north of New York City. I actually am based in Almaden, which is down in San Jose, so just the other side of the valley here. It's very close to Silicon Valley Lab, for those of you who may have been down in that area in the past. But you can see we also have a global footprint around the world. And we take seriously the fact that we're a research division and not just an advanced development shop. So we actually work very hard on advancing the science and the technology as well. So we're proud of some of the awards that our researchers have won over the years. And we actually expect them to be out, just like professors, giving talks at conferences, leading conferences, writing textbooks, in addition to patenting and open source and all the stuff we need for our products. So it's an interesting combination place to work. So our mission is really twofold. One is to be the organic growth engine for IBM. So obviously IBM also acquires companies, right? So we're very acquisitive. So that's one way we can grow, but we want to be the organic source for growth. In some cases, that's just literally helping our current product lines and getting to the next generation of Z system and databases, et cetera. And in some cases, it's starting whole new things like quantum computing. On the other hand, we actually believe we need to be really synonymous with the future of computing. And by that, I mean, not just for IBM, but just in the industry. This gets back to our role as being sort of leaders in the thought processes that go on around the world. And because we believe by being the leaders in future of computing, that will help IBM itself then, of course, maintain that leadership along the way. So if we look in the past, we've done pretty well over the last 70 years or so since IBM Research has been around. So IBM's 111. IBM Research was started in the late 40s, early 50s. We're about 70 years old at this point. And you can see just some of the things that really came from IBM itself. So DRAM came from IBM. The relational database, all of that came from actually the Almaden Lab just down south of here. The disk drive came from the Almaden Lab as well. So really we've had a long legacy of doing some of the components that are just the base of technology today. So what's next? So I'm going to talk about it in two ways. First of all, what's next in terms of what we're doing just in research to be that kind of organic growth engine. These are kind of the four areas we focus most of our research on across the global labs: hybrid cloud, AI, quantum computing, and science itself, right, to try and advance the science and technology. So just sort of a one-pager on each. In hybrid cloud, what we really focus on right now is what we call agility without risk. So it's great to say we're all in the cloud. We all know not everyone's in the cloud. We know not everyone wants to be in the cloud yet, particularly public cloud. And if you are, you're probably in 4 or 5 different public clouds. So how do we actually make this something the cloud was supposed to be, right? Which is someplace I can just run stuff, be very elastic, not have to worry about security, or not have to worry about where my data is sitting in which cloud. We're a long way from that, as any of you who work in this area know. But in the end, we really would like to be at the point when we say, hey, we can use Red Hat and we can move between clouds, that we really can, and do it in a way that the developer doesn't even have to know what they're doing, right? That literally they can just put out what they want and the cloud itself can figure out where it should be run and what's the right access for data privacy, what's the right place for even regulatory reasons for putting data certain places. All of that we'd like to make invisible to people who actually use it. So that's what we're working on the research side to do. At the same time, we're tactically trying to, of course, help just cloud itself become more efficient. Fluid intelligence is what we think about in AI. So as I'll talk a lot more in depth on what we're doing in AI right now, I think we all understand that AI is really good at some things, but they're fairly point narrow tasks at this point, and it doesn't really understand what it's doing at all. So how do we make it move from that to actually having some sort of intelligence that's more like what we think of? And what I mean by that isn't necessarily to build robots and make, amazingly Skynet overlords to take us over, but more to have at least understand more than just saying what the image is, but understand how things relate to each other. So for example, that one picture that shows some shapes right now, certainly any AI can go take a look at that and tell you there's a cylinder, a square, a hexagon, whatever. But if you asked it, what is the smallest object behind the largest blue sphere? Most AI would have no idea what the heck you're talking about, right? So how do you actually get that kind of knowledge into the AI systems? Some of it's with foundational models, which we'll talk about. Some of it's with neurosymbolic. We're kind of looking at all these approaches within the division. At the same time, we're also looking at how you run AI, because it's actually quite inefficient to run it on our current hardware. GPUs have helped tremendously, but we've got a long way to go to make it as efficient as it could be. Quantum computing, another area we're looking at. In this case, obviously, we clearly are trying to advance the quantum roadmap. I'm going to talk a lot about that in this talk, but we also talk about trying to get to frictionless development. That is, how do we make it so that everyone can start to really use quantum systems, not just quantum physicists or people really understand what's happening at the quantum level itself? And there's a lot of work to be done there, not just in the hardware, but all the software stack that goes on top of it. We take for granted in normal computing systems all the layers of abstraction that allow us to write just simple Python scripts and everything just happens and we don't have to worry about it. We're far from that in the quantum world. So how do we make that a reality? And lastly, in science, we look at many different areas, but what we're really focused on these days is how do we use computing itself to accelerate the process of doing discovery in science? How do we think about discovering new materials or chemicals more quickly? How do we think about, when you have a pandemic, trying to actually go figure out what kind of molecules will be useful for actually creating either therapeutics or vaccines? And we do think that there is this interface, this step change happening right now with what we can do with AI and normal HPC systems to help accelerate that. And over time, when quantum comes in, we think that could actually be even a larger kicker to just how you change our approach to finding new materials, new processes, new scientific advances. So that's kind of an overview of what we just do across the whole division. I'm going to dive into a couple areas here. And specifically, when we think about what's next in the future of computing, we really do think of it as sort of bits plus neurons plus qubits and how these things can combine together. So bits is really what's in today's supercomputers and computers, everything, your laptop, your iPhone, the largest supercomputers out there. But it's basically just using digital bits to represent information and process information. And of course, we know it all got put down on paper for the first time by Gordon Moore back in 1965, where he boldly took 4 points, drew a line, and said, it's going to grow like this, guys. And he turned out to be right for about 5 decades. So not a bad extrapolation from 4 points. But even today, of course, we still rely on this ability to shrink our technologies down, to get more transistors on a chip, and just to continue to advance the Van Neumann architecture of computing that we've used forever. That's the Z15, which at the time this chart was made had just come out. Of course, Z16 is about to come out here very, very shortly. But you can already see how impressive at that point our ability to do this technology was. And despite people saying that Moore's law itself is going to end, it's maybe slowing, but it's not going to end. And really what it really means is it's a lot harder to get to the next generation, and you don't get some of the same benefits you used to. Bob Denard, who's a very famous IBM fellow, came up with the scaling rules that really codified how you shrink transistors in silicon every generation to maintain your power density, but yet get double the performance, which really is quite miraculous because that doesn't happen with most things. And that physics worked really well up until about 2004 or so. And then suddenly we were at the stage where we were so small in the transistors all that physics kind of broke down because there's leakage currents and quantum effects and all sorts of stuff happening. So we no longer got the free ride of just shrink it and it'll keep going. But there's been a lot of other things we've done since to make 3D technologies, new packaging approaches. And actually, it was just last year that IBM announced the first demonstration of a 2-nanometer transistor. So that would be a transistor that could go into what we call the 2-nanometer node. Now, for those of you who actually are doing the math behind this, long ago, the nodes no longer match the size of the transistor. So this transistor is not just 2 nanometers in size. That would be quite impressive. That would only be a few atoms across or so. But it is, in fact, at a density that continues the same sort of doubling of the number of components we can put on the chip at a regular basis. And it does have many of its actual features that are literally just atoms across. So we are getting incredibly small. We had to go into 3D structure to go do this and wrap around gates and such to be able to make it controllable at this size. But we've got a lot of room happening here. And I point out that even though IBM itself does not make its own chips, we have manufacturing partners that do that, notably Global Foundries and Samsung. We did, even when we sold off our manufacturing about 5 years ago or so, we kept all of the R&D internal to us, which is very different than when we sold off the disk drive division in the early 2000s and everything went off with it. And the reason for that is we firmly believe maintaining control of our ability to do the processing and always have the leading edge process technology is critical to our systems. Even if we aren't going to sell chips to other people, we want the best chips in our systems. We think you need to control the process technology to do that. And I would say, clearly, the stuff we've been seeing with chip shortages and supply chain shortages, it's pretty clear that there's a good reason for keeping a lot of this, not only within IBM, but even within the US, if we want to think about our own sort of national security issues. So that's what we're going to do for bits. That's going to continue. It has to continue, by the way, if we want to keep everything else in the economy going well. So we will continue to keep that scaling. But at the same time, we think about what does this mean for other systems? And in particular, if we think about AI, which is probably the largest workload that's driving new advances these days, it runs okay on today's systems. It could run a lot better if we had better architectures for it. We spend time thinking about it. But first, let's talk about what we think is happening in AI itself, not at the hardware level, but in sort of the software side. So obviously, when I talk about AI, I basically talk about deep learning and deep learning networks, right? I'm not going to go through what a deep learning network is, but that's what I mostly talk about when I'm going to talk about AI in this particular talk. And of course, the remarkable thing about deep learning networks is that very recently they became really good, right? So around 2015 is when the image recognition actually surpassed human capability for doing actual recognition on ImageNet. Why that happened was a combination of data, algorithms, and compute. In particular, I would like to say it was the algorithms that researchers were really smart on. That was not actually the case. The algorithms are mostly what was used way back in like the 50s, 60s, 70s, 80s, when people first started thinking about neural nets as being a potential structure. But the reality was we didn't have compute power even close to large enough to do anything with it. So around that time, around 2011, 12, when you see the actual step function change in terms of our error rates, it's when someone figured, first of all, when we got enough compute capability to be able to actually do it. And the real insight there was the fact that GPUs do the same kind of math you need to do deep neural nets, and GPUs were really good architectures for doing it. And somebody figured that out and said, hey, let's try this. And it was amazing how suddenly you got a compute power to be able to do networks much larger than you'd ever seen before. And secondly, data. We need to have enough labeled data to be able to actually train these networks as well. And while a lot of the internet's out there, I mean, one of the reasons AI is so good at finding cats on the internet is because there are a lot of cats on the internet. So you could actually train it to find what a cat is. So maybe not the most useful reason, but at the same time, that is what allowed this whole function to happen. Now, that being said, we are spending time now in improving algorithms at the same time that we're continuing to improve the compute capacity and, of course, continue to figure out ways to get more and more data coming in. So specialized AI works quite well. So language translation, speech translation, language processing, image recognition, all these things AI can do actually really quite well, despite the fact we all get mad when we have to talk to a chatbot. And that gets to the point. It can do it really well in sort of like these almost like parlor tricks, right? I can show you how it can do this. But if I want to put it into a workflow in an enterprise or actually think about how it's going to really help me do a real business problem, it's got a ways to go. It's still right now just kind of, I can do this one function. What do I do now? And go from there on it. And the two areas that we really think about for this that have worked quite well up to now is what I call discriminative models, where you basically are giving it something and it recognizes and tells you what it is, right? And this actually is really important because this is actually basically allowing us to do on unstructured data what we've done on structured data and databases forever, which is take a bunch of information, far too much for a human to look at, and be able to come up with an answer at a scale that human couldn't do. Well, we're really good at actually recognizing dogs and cats, but we can't look at 50,000 images to do it. So how do you get a system to be able to automate that? So this has been quite useful. We've also, of course, in maybe the last 4 or 5 years, gotten much better the opposite direction. So generative models, where instead of trying to recognize something, you're trying to generate something that actually matches what you're looking for. So that could be something as simple as trying to give it a caption and have it come up with what that image should look like. By that, I don't mean that it's going to go find like a dog on the internet. It means I want a picture of a dog. It generates a picture of a dog based on what it understands a dog looks like by having looked at lots and lots of different images. So maybe that's not the most useful thing to do with it. But if you think about it like in the chemical space, we've actually been experimenting with having it see lots and lots of different molecules that have very specific properties, and then having it generate other hypothetical molecules that would have similar properties. And so you can see how that already starts to get into this idea of accelerating our ability to discover new molecules along the way, right? So there are all sorts of things we can do with generative models that we're just starting to understand and figure out how we actually build that in to our systems. So if I position where we think we are in AI today, I'm going to categorize them in 3 areas. You've probably seen these before. There's sort of narrow AI, and that's what I was saying, just the ability to kind of do these things at superhuman levels and scales that we're pretty good at. Broad AI is where we're going to try and take that and actually try and do something more useful in it from actual getting value out of it. The only place I would argue that we've actually done really well there is on selling ads to people. So there's a couple companies making a lot of money on selling ads to people with it. Pretty much everything else with AI, we're still figuring out exactly what you do with it. What do you actually do with it in a way that's going to help the average business run its operations better or generate new revenue streams? And that's going to require a lot of different things we'll talk about. And then eventually we get to general AI, which is where it starts to look like us, right? It starts to talk like us, or it starts to have this sort of sentience, I guess. Now, there was that article that someone at Google claims. I will tell you, if you ever use the system, you will not make that same claim. You'll say, no, this is clearly not sentient, not close yet, actually. And in fact, we think we're about where I show the arrow now, just entering broad. We think 2050 and beyond, probably before you really can get to something that's going to look like anything at all we'd actually call intelligent. And this whole idea of artificial intelligence is kind of just a nice little acronym, but none of it looks intelligent today at all. So to get to broad AI, I think there are several things that have to happen. And the biggest, they really are sort of just practical, which is right now we do really well when we have a huge amount of labeled data. And we have a huge model we can go build up, and we have a lot of time and money to put in to go train that model. But I can't do that for every single activity I ever want to use for AI. One, because I don't actually have labeled data for most activities I want to do with AI. And 2, I can't afford to retrain for every single application that's out there. So how do we get this more broad approach? And really what's been coming across the industry right now is this idea of foundation models. The idea, in a sense, of if you build and train a model in a way that gets large enough that it understands more of the whole area you're looking at, not just the specific task you want, that actually can suddenly be able to be reused over and over in related tasks with much less training. So if I think about what we do today, supervised learning, it's basically human powered. That is, we have to go out, get all the data collected up, we got to label it somehow, and it usually takes a human to actually do a lot of the labeling, or at least check all the labeling. And it's very long and hard and expensive to go do it. What we'd like to get to is self-supervised learning. And that's where foundation models are actually doing quite well right now, where it's much more computer powered in doing the training, requires very little labeling, and it's very automated and efficient and allows you to actually reuse itself over time. So these charts, by the way, were just shown by my boss at Dario Gil at Think, which just came out. So you can go see the whole talk there, but I'll just kind of give you a little bit of it, a little flavor of it in this case. So if you think about foundation model for language in particular, which is where these have really shown some interesting stuff. So if you think about language, it's just a whole bunch of sentences out there, right? Lots and lots of sentences, all made up of different words and different phrases. And you can think about just the terabytes of data available for it. And what you'd like to do with it is feed all that into a neural net system to train it on language, right? That's what you'd like to go do. So how do you do that without going and labeling all those sentences? So what someone figured out was, well, what you could do is have it do it itself. So it could just take a sentence and knock a word out and say, so what do you think the word is? So for example, it could take this sentence, block out the last word. It's raining cats and dry water. Nope. Dry mice. Nope. Dry deer. Nope. It's raining cats and dogs. Ah, that matches. So that's interesting because it can then take the sentences just whereas it finds them and just eliminate a word and say, okay, run it through neural net. What word do I think came out? Well, okay, I can check it myself now. I don't have to label it, but the labeling was the fact that I removed the word from the sentence. The computer can do all of that. We don't need to be involved in any of that process, right? And there's, of course, lots of approaches on how you make sure it's doing this in a way that's stochastically interesting and actually going after the right structure. But you find if you do this over and over, so give it another sentence, you guys already figured out like literally with instantly, right? It shows you how fast the brain understands exactly the pattern. It also makes you realize how much we are just pattern matching machines and how much of our own language is really quite predictable in terms of what word's going to come next. So it turns out you do this over and over and over, you eventually get to where you're really good at giving any few words what word's going to come next. And if you do it at a really large scale, like they did with GPT-3, it's amazing how much it can generate from just seeing a few sentences and saying, okay, I'm going to write a whole essay about this now. Again, it makes you wonder like how much of what we do is actually fits. That's sort of predictable, but that's interesting. Another philosophical question, I guess. But nonetheless, it actually does show that it's incredibly good at being able to understand the structure. And I'd note that this works because language does have structure. So if I just gave it a whole bunch of random data and said, eliminate one to try and train yourself on this, there's no pattern to be found. So it would not actually ever train itself to do anything. But because there is real structure in language, that means it can start to understand that structure and discover it just by doing this process over and over. So once you've got this thing trained on basically huge amounts, billions and billions of unlabeled sentences, you can then try and specialize it for what you need by training it with a much smaller amount of task-specific sentences or words that you now do label. But you're talking about labeling like thousands of them, and that actually is something that's pretty doable for most cases. So maybe you're going to try and teach it about sentiment in language, right? So instead of just understanding what word comes next, understanding that if you use these kinds of words, you're being positive about what you're talking about. These kind of words, you're being negative about what you're talking about. So that requires a human to kind of just put that in because there's nothing in the structure of language that would tell you that, right? If you understand what the words are, you wouldn't necessarily know that. So you do labeling for this kind of work. But that means you can use this model to go do various other things. I could also label the words to understand these words are molecules. These words are atoms. These words are things like this. So when you can now think about how to read this, you understand that you're reading about a molecule, and therefore that's going to be important for what you're actually searching on in that case. Again, this can be done based on the structure it already understands of language, and then just telling it about a few pieces of it that are important for the task you want. And that then makes it much more feasible to think about using this in a real business setting. We aren't going to go retrain GPT-3 every time. Instead, you're going to take that base and train it to do something specific on your task area. So we already started using this internally. Right now, we've seen 6x sort of faster improvements in doing this, 5x cheaper, which is also good for actually going and training this stuff. Not all of us have the resources of OpenAI or Google to build these gigantic systems, which is true not only of most companies, most of our clients don't either, right? I mean, it's a very infeasible thing to do unless we figure out how to really accelerate this process. And even internally, if you look at what we've been doing with our own natural language processing, before we had foundation models, it took about 7 years for us to get 12 languages going well in our stuff. In 1 year, we got 13 more languages going on because suddenly you've got the structure and understanding of how you build these models, and you can rapidly take it even into other languages. It turns out that the structure of languages is remarkably similar across different language classes, even though it's very hard for us to learn different languages. Turns out there's a lot of similarities in the structure of them when it comes to an AI might learn them. So we can use it for languages, and we can also use it for other things. We could use it for chemicals. So I talked about discovering new chemicals with generative models. Well, maybe I want to build a foundation model that really understands chemistry, like really has seen all the stuff out there. And again, there's lots of data in the literature and things on chemistry. If I don't have to label all of it, it can actually try and learn this stuff. Or maybe I want to have it understand things about customer behavior. One of the things that we're actually focused on right now in research is how do we apply foundation models to actual problems and data our clients might have. And one good example would be when you think about trying to get customer behavior or understand customer interactions. So you have lots and lots of tables out there of data about our customers, right? Like maybe these are columns of what all the products a certain customer bought, or their particular attributes, demographics, and then what they tended to do in different days of the week or different times of year. Whatever you have in your database right now, we of course use business analytics to go through and understand and try and use this for making predictions as to what's going to happen. But if you look at this looks a lot like language, right? You have rows of this, which could be think of as sentences. Each row has individual components, which you could think of as words. Those entries are just words in a sense. So you can do the same thing you do with foundation models. Just take those and feed it in and block off certain ones and say, what do you think this cell is? Given the other cells, what do you think that cell is? And it can, of course, train the neural net over time to say, okay, I'll try this, oh, and it finds it. And little by little, it starts to figure out what each of the cells are. And when you're done, it's now got an understanding of basically your entire structured table here in a way that's different than what the business analyst can just go do to do simple regressions and things on it. And so we think this is a way then we can actually utilize foundation models to make advances in understanding other parts of data that aren't just language itself, but maybe customer behavior or other types of activities. So that's good. I think AI, we see some ways that we can get AI to be a little more applicable in more sort of business environments. In fact, AI, of course, is going to be used more and more for making decisions in fairly maybe more important things than just whether or not I made the right recommendation for you for which movie to go get, such as making a decision on your credit score or your employment or justice kind of things, which does bring up a lot of the questions of ethics, which we do spend a lot of time on. So when we think about making sure our AI is sort of ethical, there's sort of two components. One is really just trying to think about the AI itself, with the things we're putting out there. Is it fair? So that is, are the other results that are coming out of this unbiased? That in itself is a very difficult question because fairness does depend on what you're trying to achieve at any given moment. There's different kinds of fairness. There's a great article actually in Vox about 6 months ago that talks about the 21 or 24 different types of fairness. And you can read through them really quickly. It's very funny because we read each one, you're like, oh yeah, that's fair. Then you read the next one, oh no, that's fair. You're like, wait, those two are mutually exclusive. I can't do both those things, right? And you realize that even as humans, you have to trade off. There's always a trade-off when you mean by fair at any given moment. It might be fair to an individual. Is it fair to the group? It might be fair to the group. Does that just exclude a subset of the group and certain individuals? You can think through how quickly there's an issue there. So we believe that finding ways to have the AI be able to at least surface up which biases and what things are happening along the way, a lot like what our AI 360 toolkit tries to do, for example, is important because it's really a human who's going to have to make the decision and trade off on what is fair for the situation we're looking at. That means you have to understand the answers that the AI is giving you. It can't be a complete black box. So we continue to try and work on how to make that more transparent so you can understand why it made the decisions it did. Obviously, making sure it's secure. There's been a lot of articles on how you can actually trick AI very easily at this point. Even not having access to the source code or being able to retrain it just by figuring out what it's recognizing it. Because again, it doesn't really know what it's recognizing. It's just finding some bit patterns and saying this is what it is. So that's a big issue. And of course, is it accountable and transparent? So that is, do we understand a way that if something gets made wrong, can we go back, trace why the decision comes out from it, and then have an accountability as to how we can go get that corrected? So that's one aspect of trust. The other is thinking more broadly. And there's a research group under me that focuses on responsible and inclusive technology. So this is now going beyond just making sure things aren't biased, which is a good thing, but also how do we make sure that it's actually inclusive for people and actually is being responsible in what's going out there? And so even like in quantum computing, we're spending a lot of time thinking, are we really putting this out inclusively? So in a sense, it's free on the cloud for everybody. Anyone can go use it. That seems really inclusive. Assuming you have a computer and a good high bandwidth connection to the internet, and you understand enough about quantum computing and programming to actually get access to it. So you rapidly realize it's not particularly inclusive. It's really inclusive to people who live right here in this area. That's great, but not for most of the world. So how do you actually think about getting it out in a way that truly is reachable to folks? And how can you actually use technology itself to actually eliminate bias? So use it proactively, because we know that humans themselves are biased. So it doesn't mean that we have to just replicate what humans do. Could AI systems actually, because they are at least in theory unbiased, if you give it data that's unbiased, could that help humans actually become less biased in some of the decisions they're making? That was one of the original hopes of AI before we realized, of course, that when you teach AI based on our own data, if our data is biased and the AI is biased, how do we get around that problem? So we're spending time on that in our research group as well. Okay, so last topic on AI, as I mentioned before, so this working really well, these models are really big. So it turns out they're really, really big. So really about 2x every 3 months is the amount of size and training it takes to continue to get these larger and larger models. And if you look at GPT-3, it took 175 billion parameters it was running, 310,000 exaflops for training. So, months and months, tens of millions of dollars it costs to train this model, right? And by the way, 550 tons of carbon dioxide were emitted in the process, right? So that's like 3 jet, not passenger planes, back and forth from New York to San Francisco trips. So it's got real problems, not just for the cost of energy and the heat and all that stuff, but also the actual carbon outputs as well. So clearly we need to find a better way on this. And so we try and think through how we can actually innovate on it. Obviously, there's a lot of work going on already, just in the algorithm level, software level, all those sorts of things. But we actually also are spending time at the base hardware level thinking about this. So a few years ago, we launched the IBM Research AI Hardware Center in Albany, New York. We have lots of different partners and members from across the semiconductor industry. And its focus is really specifically on how do we build semiconductor chips and systems and such that actually can run AI itself more efficiently. Now, I mentioned the GPUs were really the breakthrough that allowed us to get where we are today. And as I also mentioned, it was just dumb luck. It just turned out that the math you need for the graphics, which had a great, huge market in gaming, so they can make lots of money selling those chips, also works for AI. So that's great. NVIDIA got very lucky. That's good. We can maybe do better than luck. Let's actually see if we can actually design something that will work along these lines. That's what this group is working on. And just in a nutshell, we do believe there's a really orders of magnitude capabilities of being able to improve what we're seeing for performance on this. Right now, we focus most of our time on is thinking about improving the architecture, because just because GPUs are good at it, they aren't the optimal architecture if you're really talking about doing AI, deep learning, and also realizing that you don't have to have the accuracy we're used to. So up till now in high performance computing, you're always like 32-bit, 64-bit, 128-bit, floating point operations, which is great if you're trying to do really, careful physics kinds of simulations. The brain is at roughly 4 bits of accuracy from what we can tell, give or take, depending on who you're talking to and who you're talking with. But at the same time, it gets really good at doing image stuff, right? Because I don't care if every calculation of the deep neural net was accurate. What I care about is if I look out at a window and I see a woman walking towards me, that I can say, oh, that's my mom, right? That's all I care about. Did I get mom right? The accuracy of my brain didn't matter, right? And in fact, even when the mirror is blurred or there's fog on the window, you're only getting a few bits of accuracy even coming in from the window, I'm still really good at saying that's my mom, right? And it didn't make any difference to me that the accuracy was wrong in the image that was hitting my eye. So we are looking to really reduce this tremendously. We've already gotten down to 8 bits of 8-bit floating point, and even 8-bit integer calculations can still be almost as accurate as what we've seen that you can do with full floating point. And if you talk about inferencing, you can go down maybe even to 4 bits, maybe even 2 bits. We'll see along the way. But that every time you do this, you gain by a factor of 4 in power and area when you reduce by a factor of 2 in the bits. So you've got a huge lever there going forward. We're also looking at how we actually embed these into systems. The Z16 chip that's going to be out actually has an AI inference core that came from our AI hardware center embedded in it to really be able to do AI inferencing. So that is, not training it, we'll get trained someplace else, but inferencing for all the transactions going through on the fly in real time. So you think about that, you're a bank and you're doing millions of transactions a second and you want to look for fraud. If you've been doing AI right there next to it to look for patterns and immediately say, wait, that transaction just went through a second ago, there's a problem with it, versus instead doing something batch overnight to go back and look through and say, okay, all the transactions, anything look funny here, let's go back and figure it out. It's obviously a huge advantage. So I think that's going to be something else we'll be working on. Beyond that, we're looking at completely different technologies. So if you're going to say we don't need to have 32 bits of accuracy for the floating point, do we need to necessarily even stay digital? We know that the brain neurons are not digital, they're analog, obviously. So could you go back to using analog kinds of structures to have the same kind of effect? And the answer is yes. We've done some analog neural nets already that actually can show almost the same accuracy as you get from a digital neural net. You can save up to 100x or so in power just by doing some simple stuff we're doing already. We think we can do even better. We know, by the way, the brain is at least 10 to 100,000 times more efficient than what we're seeing today. The brain is only about 20 or 30 watts, so it's a amazingly efficient system for doing this. So we think this is another direction to pursue, and we're going to see where that goes. And then ultimately, we also are looking at quantum computing. We do think that there will be some AI problems where quantum computing can have an impact. We're still learning what those might be, but certainly that's something else we keep on the roadmap. Which leads us then to quantum computing and qubits, the last part of our group here. So just quickly, I think we already talked about bits. Everyone knows what a bit is. It's a 1 or a 0. It's the basic unit we use for doing computation. We have classical logic circuits, NANDs and NORs and things like that actually go and do logic on those. And of course, from that, we build up everything we see today. So in a qubit world, same thing, except in this case, it can be a 1 or a 0, or it can be a superposition of probabilities between those two. We'll talk about what that means. And then we'll build a quantum circuit. And a quantum circuit will take and have gates similar to a NAND and a NOR, not a NAND and a NOR, but similar to those. And we have a universal set of gates that can let us do all logic operations as well. And that's really the kind of structure we're looking for a quantum system. So for the qubit itself, the thing that makes it interesting is the fact that it's a 1 or a 0, but it's representing it with a quantum state. So a quantum state doesn't have to be absolutely a 1 or a 0. It can actually have a probability of being a 1 or a 0 at the same time. So it could be 80% chance of being a 1 and 20% chance of being a 0, for example. So that superposition allows you, in a sense, to sort of test both those at the same time. That's not actually what's happening at all, but you just think of it that way. So sort of a massive parallelization going on. Even more importantly, though, you can actually entangle the qubits. So you can take one qubit and put it in a superposition, and you can take another qubit and put it in a superposition of 1s and 0s, and you can entangle them so that when you measure one, and it's whatever you measure it, it'll tell you 1 or 0, by the way. It doesn't tell you like a half. It'll say, I'm a 1 or a 0, but when you measured it, the other one instantly takes a known value and may be the same or different depending on which gate you use to entangle them. And in fact, this is true no matter how far apart they are in the universe. This is the thing that Einstein hated about quantum mechanics, because it doesn't really make sense that is the case, but we know it's true. And we've seen it actually demonstrated at very far distances in the past. But for quantum systems, all we care about is what if you can entangle a huge number of these qubits? So in a sense, as you're operating on one, you are in a sense operating on all of them. And you can use this to try to actually determine very large problem spaces. And that's really the key for quantum systems, and why we think they're more powerful is the number of states you can represent at once and test at once. So if you think about our classic computers, we talked about Moore's law. Every time we double the number of transistors on the chip, we roughly double the performance of the chip. It's not one-to-one, but if you look at it, it's a pretty darn linear line in terms of how this happened. So we go up by a factor of n. On the other hand, in a quantum system, every time you add a qubit, you actually get 2 to the n more states, right? Because it can be in the superposition and be entangled. So that's pretty powerful. If I start with a 5-qubit system, that's 2 to the 5th, 32 states I can represent. If I had 10 qubits, I can now represent 1,024 states. So double the number of qubits went from 32 to 1,024 states, right? Exponentials are very powerful, right? So suddenly you could represent a much larger space of possible answers at once, and then go and, of course, actually compute down what the right answer is from that in a way that, from interference of the different solutions, to actually come up with what the right answer would be. So let's just give an example of why this might be important. And we're going to start with caffeine because it's a molecule everyone loves. It's actually a fairly small molecule. It's got 95 electrons. But it turns out that if you wanted to actually use a supercomputer to compute exactly the ground state of this molecule and all 95 electrons, all of which are quantum entities themselves, it would require 10 to the 48 classical computer bits to represent all those possible states. And that's just what that looks like written out. It's a big number. And when I say big, by the way, the planet Earth is estimated to have about 10 to the 50 atoms in it. So you need about 1% of all the atoms in the planet Earth to represent one of your states for you. So when we say you'll never build a system this big, we honestly mean you will never build a system this big. And this isn't even that large of a molecule, right? It would only take 160 qubits if they were, error-free qubits and perfect qubits, which, by the way, we don't have yet. But if they were, it would only take 160 of them to go do it. So we just put out a chip last year that has a little over 100 qubits. Again, they aren't high enough fidelity yet to actually do this directly, but they are getting there, and that's getting very close. So we will have systems that can do this, we think, within 2 to 3 years, right? That they can start to actually do something that's interesting that you really can't do on a classical system. So Well, like I said, we started this back in May when we put out the very first system on the cloud. It was only 5 qubits at the time. At this point, we have over 24 systems out running in the cloud, some for free, some for our partners and members. You can see the number of circuits that have been run on them. That's what the system looks like on the outside. Inside, for those of you who haven't seen it before, they really are quite beautiful, these quantum systems. The chip itself at the bottom there is actually the actual quantum computer. Everything around it is otherwise cooling, support, wires going in and out, everything to actually run the system along the way. This whole thing is encased in the dilution refrigerator, which keeps it at a very cold 15 millikelvin at the chip itself. So that's about 15 thousandths of a degree above absolute zero. So very, very cold. Outer space is about 2 Kelvin. So it's about 200 times colder than outer space. It's an amazing feat. Just do that on its own. But it's necessary for keeping the coherence of those states. That superposition and entanglement I was talking about, anything at all that measures it, means like gets jostled by a photon of temperature or the photon of electricity, it will immediately choose a 1 or a 0. It will never stay in that quantum state. So we have to keep it well isolated to do this. Kind of problems you can do with this. So if you think about the world of problems you can solve in general, there's a set we call the easy problems. By easy, I don't mean that you can do them in your head. I mean that you can prove mathematically that these are problems that don't grow exponentially with the number of inputs going into them. Build a big enough supercomputer, you can eventually solve the problem. That's great. Hard problems are ones that don't fall into that category, that there are ones you can show mathematically that just the number of things you have to test grows exponentially with the inputs. Traveling salesman is a good example of that kind of problem. It grows exponentially as you put it in, so you can't ever build a system large enough to go solve it. A subset of the hard problems are what we call quantum possible. That is, they map well onto a quantum architecture. Not all hard problems do, but some actually do. And those are the ones that are really interesting then, because if you can actually get something there that you can never do classically, but you could do in a quantum one, that's very interesting. By the way, this traveling salesman problem is not one of those, it turns out. The actually unconstrained traveling salesman problem cannot be mapped efficiently onto a quantum system. There are constrained versions that are really important for optimization that can, in fact, be mapped on. So they would fall in that quantum possible range. So those are very interesting to many companies, but the full one actually just turned out you can't do it. So applications, chemistry, materials, any place that you want to actually simulate a quantum system itself, quantum computers will have the first impact, right? Because I think in that case, whether you're trying to find new materials or molecules, you'll be able to do well on it. Optimization problems, machine learning problems, all of these we think have a capability potentially there as well. Factoring, yes, factoring is another one you could do stuff on. Cryptography obviously is one that people are concerned about. It is true that a large enough quantum system could break the cryptography that we use today. That's well known. We have probably a good 10 years before we get a system that's large enough to really do any factoring that anyone would care about. And already, though, we know the answer in a sense. We already know how to do cryptography using classical systems that does not map on to a quantum system well. So that being those other sections of hard problems. Lattice cryptography, for those of you who know what that is the version or is the class of problems that we look at for this. So we already are working with clients on, hey, you probably want to start encrypting your stuff, your archives, using this type of cryptography, because then when someday someone has a quantum computer, they're not going to come after your archive tapes. But in terms of worrying about the internet breaking down, we got a ways to go. So application areas, these are just a list of some of the application areas that are exciting for quantum these days. And you can see we have a lot of different people working in different ones of these, different partners as well. We have a roadmap that just came out that we were very clear on what we're doing. We've been working on this for the last 4 or 5 years. You can see 2023 is when we're going to hit approximately 1,000 qubits. That's when things start to get interesting in terms of being able to maybe do things that you can't do with a classical system today very well. The current systems we have are so small that yes, you can prove that you can do something interesting, but you still can do it easier with a classical system. So you need to get to a certain size before that matters. You can see as we get over time, we actually start interconnecting chips as well and make that quantum coherent. That'll be exciting. Very, very hard science challenge. We're working on that. And we also have all layers of the stack up on top for the actual software and things that are necessary to make this all work. And that's something that we actually involve a lot of people in the open source community on as well. This is what the picture of the system we think will be at for system 2 in a few years, to actually interconnect even between quantum systems to really build quantum computing supercomputers. So the 3 things we need to get there: scale, which is just the roadmap talks about the number of qubits we need to build up, and we've got a roadmap for that. But equally important is quality. we've got to be able to reduce the error rates on these qubits at the same rate at which we're increasing the number of qubits, or else these will not be efficient. And that turns out to be the biggest issue for us right now. These qubits are small, but they aren't that small compared to like the 2 nanometer chips we make, right? It's just a question of we can't use them efficiently if there's the error rate's too high, because you won't be able to get everything set up all entangled and in superposition the way you want it before one of them starts getting an error and decohering and becoming classical again. So we continue to increase that quality rate as well. It's measured by something called quantum volume, and some interesting papers on that if you're interested in knowing what that actually entails. But think of it as error rate's got to go down. That's basically the answer. Speed is the last thing, how fast these things actually operate. And this is one where we believe superconducting chips are particularly important. Trapped ion is one of the other technologies that's out there. Honeywell has a really very nice system that uses trapped ion. It actually has a higher quantum volume than ours in many cases. It's very slow. The amount of time it takes to flip a spin in a trapped ion is, in the order of maybe millisecond or so. You can do the math on how fast you can really run a system then. We're probably about 100 to 1,000 times faster when you flip a superconducting qubit. That's going to be really important if you actually want a real problem. So this idea of what we call circuit layer operations per second is going to be a key differentiator. I mentioned the software side, Qiskit. Qiskit.org is the open source site for this. All of our software that we're using for developing on this is open source. We really want a huge ecosystem of developers and community to be using this and building up. There's a lot of things we don't know that we're going to need to actually make systems usable. In the end, we want somebody to be able to just be completely frictionless in this, right? You should be able to develop on a quantum system with the same tools, languages, and code that you would use to do a classical system, right? And we aren't there yet, to say the least. But we need a lot of work on the software side to make that happen. And really at 3 different levels. Kernel developers, people who literally do understand what's happening at the circuit level and understand how you build a kernel of a circuit that could actually then be used by an algorithm developer to build out an algorithm, where the algorithm developer doesn't necessarily have to understand exactly what the best way to lay that out is in the quantum architecture you've got on the chip, the same way that none of you worry about what the NAND/NOR architecture is on the chip you're using when you program a classical system. And then eventually we want to get to model developers who can then take the algorithms and build up libraries for people who I'm just a chemist. I just want to go run a chemical simulation. I don't want to have to program anything. I just want to put out a script and then you guys can figure out what I'm supposed to go do with this in a library call. So that's what we'd like to get to, and that's why we have this all open source to have other people out there helping us build it out. And by the way, we expect it to run on other people's hardware too. We aren't saying it has to only run on our hardware. It's open source. It runs on trapped ion and other things as well, because that's going to be key to making the quantum ecosystem really effective. So the quantum systems are out there today. We have people using them every day. This is just kind of a real-time mapping of it. The blue is actually running on our hardware, which is mostly in the Poughkeepsie data center in New York. The red is the simulations that people can also run using that same architecture. You can see it around the world. We have people on all 7 continents, including Antarctica. There was a woman down there who actually, long winter, I guess, isolated in Antarctica, taught herself how to use quantum computing. And we saw the pings, we're like, that can't be coming from there, but turned out it was. So anyway, it's interesting to see where people actually get excited about it. Lots of partners right now, big partners, big companies who are interested in working on this with us, that actually are working on various algorithms. Lots of universities, of course, as well as startups. We have a very active startup program to let people get access to some of what we do when they're building their usually software-based startups is what we mostly are focused on. So all that together, bits, neurons, qubits, that's where we see the future of computing going. And I think that when you really combine them, we're going to have what we're going to call a really hybrid cloud, right? So not just hybrid cloud like we think today, but really hybrid. And the idea of being able to program that and figure out how you actually efficiently combine a quantum system with a classical system, maybe with an AI system to solve really hard problems, is itself a really hard problem, right? So it's not going to, your average programmer shouldn't be expected to figure out how they're going to actually utilize all this. They should be able to be putting together the problem they're trying to solve, and then the system should be able to help figure out where you would send the various parts of that problem, break it down in a way that makes sense. We're already making some progress on that in the quantum side, because it does take a lot of interaction between the quantum system and a classical system. So we have something called Qiskit runtime, where it actually goes and sends your problem up to the system. There's a co-located classical system where the system breaks apart, then the classical part, the quantum part, but they're very, very tightly coupled, so very low latency. So you can actually go back and forth and get the answer about 100 times faster than you could have the way we used to do it the first time through. So this is going to be really important for us to actually go and produce. So the last point I want to make before I close off here is I mentioned accelerated discovery as being something we really think is an important use for this new combination of bits, qubits, and neurons. So let's just look at material design and discovery. If you want to discover a new material, you can go back and look through the literature. It's almost always about a 10-year process. You look at copper interconnects that we did at IBM. You could look at a drug molecule, which, by the way, you could add another zero to the cost on the drug molecule. It's still about 10 years, but it's more like $1 billion, not 100 million to get it out the door. So that's great, but that limits your ability to go forward on it. We want to really aim to get it down by about 10x, 90%. We believe we believe it's doable for some areas. I'm not going to say materials discovery is something that become 10 times faster for everything, but if you think about the kinds of things you do in the process right now, it's still mostly very Edisonian in that you just come up with ideas for materials, you make the material, you try the material. You can do some simulations, but our ability to simulate materials on even high-performance computing systems is pretty limited. We saw the caffeine example. It's pretty hard to simulate large molecules or even large material or atom systems interacting very well. AI might help there, by the way, even before quantum does. Those of you who saw the protein folding stuff from AlphaGo, that's pretty impressive because we can no way get near actually simulating protein folding on large supercomputers. But an AI system got pretty good at figuring out what the structure would be of a very complex protein based on being trained on a large number of them. So lots of things we think can help there. So we want to actually help throughout this whole process, from learning, hypothesizing, testing, iterating. So it's clearly just AI capability for searching is huge, right? The average researcher can read a couple dozen papers, I don't know, a week, maybe if they're lucky. Maybe they can do more than that. But if you actually read all literature, but understanding what a molecule is, understanding what a reaction is, not just keyword searching, which of course we can already do, that can make a huge difference to actually surface up the right papers to a researcher to actually understand the connections that they're looking for. That faster ways of actually doing screening on the things along the way. So you can quickly look at a database and understand what may or may not actually be applicable for where you are. Again, a human can do this, but not at the scale an AI system could potentially do it. And that's what we think can make the difference. But even generating hypothetical molecules, as I said, we actually did an experiment for photoresists where we had to generate ideas for photoresists. And it came up with several molecules that were quite interesting. We tested in the lab, and a couple of them actually turned out to have some properties that we were looking for that we hadn't found on our own yet. So there's definitely evidence this can happen. And finally, of course, actually synthesizing along the way. I'm not going to go into this, but if you're interested, look at the 5 and 5. Came out last year. It actually gives some examples of where we think accelerated discovery can help on some really big world problems: carbon capture, production of food and fertilizer, discovering new materials that are more sustainable and earth-friendly, not just higher performance, thinking about ways to improve our own manufacturing stability, our sustainability in our own chips, battery technology, and also then drugs and molecules. Obviously, that's a big deal that came to us all during the pandemic along the way. So I'm going to just end on this chart. This, if you're interested, is something we just released about 2 weeks ago. It's we call it our IBM Research Technology Atlas. You can see the URL up there for it. Basically, it's a roadmap of all the stuff we're working on and how it interconnects together. So you can see systems, quantum, security, hybrid cloud, AI, semiconductors. Those are our main topic areas. If you click on one, it shows you how it also interconnects with others. It shows you what we think our roadmap is for the next 2 to 3 years out on the circles there. And if you go down and explore the roadmap, you can actually see what are our high-level goals for each of those areas. Now, this is publicly available, so it's the publicly high-level goals. So, if you want to learn more about it internally, of course, you have to reach out to somebody within research. But it does give you, I think, a really good overview of what we're going, what we think is happening right now. So I encourage you to take a look at any time, and hope you enjoyed learning a little about what we think is going on in IBM Research to the future of computing.
Debbie, did we have one quick question from the WebEx? Oh, and we have one question on here.
Go for it. Yep.
Cloning principle, it's kind of difficult to scale.
Yep. So I'll repeat the question. So the question is what we're doing right now for scaling on the quantum systems, how do we take into account error correction, which is a huge issue for us right now? Yeah, so at the same time we're trying to get the error rate down, we absolutely believe you will never get the error rate down low enough. You will absolutely need to use error correction or error mitigation, we would call it. And there's various different ways of doing what they call topological codes to try and figure out how you could actually do this. So you think about it in classical systems, we do it just by doing redundancy, right? You have like you have checksums and you have extra bits and stuff to make sure your memory is doing the right thing. You can't do that in quantum because you aren't allowed to copy quantum information or clone it in any way. So you can't actually just make a second copy of it. Instead, what we try and do is you take maybe a dozen qubits and use them to represent one logical qubit. And there are very specific ways of doing interactions between them that allow you to do this without making you actually copy something from one to another, and allows you to test some of them without destroying the information in other parts of them. It's all very theoretical at this point. I shouldn't say theoretical. It's being done, but we don't know what the right answer is. We don't know. And probably the biggest question is, could I do it with just 10 qubits equals 1? Do I need 100 qubits to equal 1 qubit? Do I need 1,000 qubits to equal 1 qubit? Clearly, if you get to 1,000 qubits to equal 1 qubit, that's a very different level of qubit number you need before you're going to end up with a efficient system. So I think that's one of the biggest open questions.
I saw the AI presentation and I was wondering, for sparse data, the AI system currently, we have a language modeling system, and do we have sort of ontology sort of built out for say certain domains to get that language models even more like accelerated, because some sort of ontology or structural ontology would be helpful in having some sense of understanding of say a certain domain.
Okay. I understand what you're saying. I don't know that I have a good answer for you right now. If you want to send me an email afterwards, I can try and hook you up with the right folks on it, because I think through it, there's a couple places it could go, but I'm not sure I really know a good place to send you right off the top of my head. Yeah, good. Question, sure. No.
So you mentioned caffeine and 160 qubits, and then you mentioned that we'll probably get there. So are you talking about 160 error correction in 2 or 3 years?
So, okay, yeah. So the question is, when I talk about 160 qubits, and we'll be there in about 2 or 3 years, but I also mentioned you have to have high quality qubits. Yes. So I was actually mixing two things up at once. I should say conflating a couple things. To actually do exactly what I said, you would need 160 completely error corrected qubits. We will not be there in 2 to 3 years. We don't know when we'll be there. However, the reason we think materials and chemistry is the right place to go after, those kinds of problems are very fault tolerant in general. So one of the things we're experimenting with is, okay, so maybe I need more than 160, but maybe I don't necessarily have to have a lot of error mitigation on it. Maybe I can find a way to map it on to a larger number of qubits in a way that, okay, I'm not getting quite the right answer, but by testing it over and over, I can get it. We already did a little proof of concept of this. We did did a very simple lithium hydrogen molecule, right? Just very easy, by the way, you can do it on a classical system, but we used one of our early qubit systems because it only took a few qubits to actually do that. And you got the answer. It was fairly far off because of the noise. But what we realized is we could actually artificially inject more noise in, and you can see how things moved. And then if you extrapolate the other direction and say, well, if I went this way, then you could actually extrapolate back down. Well, if I had zero noise, this is what it would have given me as an answer. Turned out that was incredibly close to what the right answer is. Because again, that one we can simulate exactly at a normal system. So by playing tricks like this in problems that are amenable to that, it's good. If you're trying to do optimization or you're trying to do some of the stuff in machine learning, it's not clear or factoring, for that example, it's not clear you can live with that kind of error stuff. But we think in the materials and chemistry space, you'll be able to get away with it.
Same thing. So I mean, right now, classical systems, hexagonalization is pretty.
Yep.
So how far, even error mitigation, extrapolation, and so on, actually doing 40 fermions.
I don't know if I can. It's actually when I can actually get to 40 fermions and actually do it well. Exactly right. It's a good question. We were basically saying roughly the next couple of years. Once we get over about 1,000 qubits total, and we extrapolate what we think our error rate will be at that point, and our evolving understanding of how well the algorithms work and how we can improve those, that's kind of our point. But when I say that, I'm not going to say I'm going to get to 40 fermions in a couple of years. But that's when it starts to get a fluctuation point. Yeah.
Yeah. Thanks.
stood out, just because I know it's what's going on at Amazon, is that you had for time this idea of brain-inspired computing. And where does that fit? Because you didn't mention it. Is it just because the timing, you didn't have enough time to talk about it? Where does it fit?
We are still looking at that, actually, not in our mains. So the question was how we're looking at brain-inspired, truly brain-inspired architectures. And the answer is sort of twofold. The stuff we do like at the AI Hardware Center, at least looks at what the brain's doing, particularly in some of the analog materials that we're looking at, because that looks much more like a brain in terms of the analog kind of functions. So I'd say we take a little inspiration from it, but we don't really try to actually model or reproduce the brain. In parallel, we have some more exploratory science work going on in Zurich and a little bit in Almaden as well on what if you want to have a spiking neural net, like something that really is like the brain uses spikes that go around. Can you get advantages on it? In fact, we did a challenge on the spiking neural net we put out publicly from Zurich last fall, where we put out some tools that people could go to emulate these things and see how well you could actually build an algorithm to go do certain problems using a spiking neural net, and then extrapolate how efficient that would be if we actually had hardware that did it. So we're still playing with it. I think at this point we don't see anything yet that we're going to say, oh, that's how we're going to go do it using the way the brain does it. But we're doing that kind of in parallel. Okay, I think that's it for the questions. Sorry.
But Jeff will be
I'll stop
around.
here, yeah.
We're having pizza. I just want to, for the people on the WebEx. So I just want to close, and I just want to thank Dr. Jeff Welser again for a phenomenal talk and the amazing work that IBM Research is doing. And these are types of, a lot of our Academy of Technology members are at IBM Research. So in terms of our working with them, maybe there's some initiatives in some of these amazing areas. And we can't wait also for next year that you come and see what other amazing things IBM is doing. So thank you very much.
Thank
Okay,
you.
so with that, we're going to close the WebEx.